So here's something worth thinking about as you settle in tonight. Every single thing that has ever left this planet, every rocket, every satellite, every probe drifting right now through the outer solar system, all of it traces back to a very simple, very old idea. And that idea is this: if you throw something hard enough, it doesn't come back down. That's it. That's the seed of everything. And people figured that out a surprisingly long time ago, centuries before anyone had the faintest clue how to actually do it. But let's not rush. Let's start even further back than that, because the story of space exploration doesn't really begin with rockets. It begins with looking up. It begins with the fact that human beings, for as long as we've been human, have stared at the night sky and wondered what was up there. And you're doing something right now that connects you to every single one of those people. You're lying still, maybe in the dark, and if you let your mind drift upward, you can almost feel that same pull, that same quiet curiosity. What's out there? The ancient Babylonians were some of the first people we know of who did more than just wonder. Around 1800 BCE, maybe earlier, they started keeping detailed records of what they saw in the sky. Not poetry, not myth, actual observations. They tracked the movements of Venus with remarkable precision, scratching their findings into clay tablets in cuneiform script. And here's what's clever about what they were doing. They weren't just watching, they were predicting. They figured out that certain celestial events repeated in cycles, and they used those cycles to forecast what would happen next. That's not mysticism, that's data. That's the earliest version of the scientific method applied to the cosmos, and it was happening nearly 4,000 years ago in what's now Iraq. The Greeks took it further, of course. Around 240 BCE, a man named Eratosthenes, he was the chief librarian at the Library of Alexandria, which is already a pretty great job title. He figured out the circumference of the Earth. And the way he did it is just beautiful. He knew that at noon on the summer solstice in a city called Syene, far to the south, the sun shone straight down into a deep well with no shadow at the bottom. But in Alexandria, at that same moment, a vertical stick cast a shadow. He measured the angle of that shadow, about 7 degrees, and he knew the distance between the two cities, roughly 800 kilometers. A little geometry, and he calculated the Earth's circumference to within a few % of the actual value. Think about that. No satellites, no telescopes, no computers. Just a stick, a well, and a very sharp mind. And suddenly, the Earth had a size. It was a real, measurable object, not an infinite plane stretching out forever. That changes everything about how you think about what's beyond it. Then there's Aristarchus of Samos, working around the same era, who proposed something genuinely radical, that the Earth goes around the sun, not the other way around. He was right, obviously, but almost nobody believed him. The idea was too strange, too uncomfortable. It would take almost 1,800 years before Copernicus came along and said the same thing, and even then, it caused enormous controversy. But Aristarchus had the insight. He even tried to estimate the relative distances to the sun and moon using the geometry of lunar eclipses. His numbers were way off. The sun is about 20 times farther away than he calculated, but the method was sound. The thinking was right. He just didn't have precise enough instruments. And that's a theme you'll see over and over in this story. The ideas often come long before the technology to test them. People figure out what should be true, and then they wait, sometimes for generations, until someone builds the tool that can prove it. Now, let's talk about the moment when looking up started to turn into reaching up, Because for most of human history, the sky was something you observed. It was a map, a calendar, a source of stories. But it wasn't a place you could go. The shift from observation to aspiration, from watching the heavens to imagining yourself traveling through them, that's a more recent development, and it has a surprisingly specific origin point. In 1687, Isaac Newton published the Principia Mathematica, and buried in that dense, brilliant, sometimes infuriating book is a thought experiment that basically invented the concept of orbital mechanics. Newton imagined a cannon on top of a very tall mountain, firing a cannonball horizontally. If you fire it gently, it arcs down and hits the ground nearby. Fire it harder, it travels farther before landing. Fire it hard enough, and something remarkable happens. The cannonball is falling toward the Earth, but the Earth's surface is curving away beneath it at the same rate. The ball never lands. It just keeps falling forever in a circle around the planet. That's an orbit. That's what the International Space Station is doing right now, about 400 kilometers above your head. It's not floating. It's falling. It's just moving sideways so fast that it keeps missing the ground. Newton didn't have a way to actually launch anything into orbit, of course. The idea was purely theoretical. But he gave humanity the math. He showed that the same force that pulls an apple from a tree is the same force that keeps the moon circling the Earth. Gravity isn't just a local phenomenon. It's universal. It works the same way everywhere, at every scale. And once you understand that, once you can write equations that describe exactly how objects move under the influence of gravity, you can start planning trajectories. You can start asking questions like, how fast would something need to go to reach orbit? How much energy would that take? What kind of force could provide that energy? The answer to that last question, it turns out, had been around for a very long time. Rockets. Simple, crude, beautiful rockets. The Chinese were using gunpowder-propelled rockets as weapons as early as the 13th century. During the Battle of Kai Keng in 1232, the Song dynasty reportedly used arrows of flying fire against Mongol invaders, essentially tubes packed with gunpowder attached to sticks for stability and pointed at the enemy. They weren't precise. They weren't particularly reliable, but they worked on a principle that would eventually carry human beings to the moon, Newton's third law. Every action has an equal and opposite reaction. You throw hot gas out the back of a tube, and the tube moves forward. That's it. That's how every rocket that has ever flown works, from those 13th century Chinese fire arrows to the Saturn V. And here's the thing about rockets that makes them special, the reason they're the only technology that can work in space. Every other form of propulsion we've ever invented relies on pushing against something: a road, water, air. A car pushes against the ground through its tires. A boat pushes water backward with its propeller. A jet engine sucks in air, heats it, and blasts it out the back. But in space, there's nothing to push against. No air, no water, no ground. A rocket doesn't need any of that. It carries its own reaction mass, its propellant, and throws it backward. It pushes against itself. It's the only engine that works in a vacuum, and that's why, despite all our technological progress, we still use rockets. We've made them enormously more sophisticated, but the fundamental principle hasn't changed in 800 years. For centuries, though, rockets remained weapons and fireworks. Nobody seriously thought about using them for travel, let alone for reaching space. That didn't happen until the very end of the 19th century, and it happened in one of the most unlikely places imaginable, a small wooden house in rural Russia, where a nearly deaf schoolteacher was about to change everything. His name was Konstantin Tsiolkovsky, and his story is one of the most remarkable in the history of science. Born in 1857 in the village of Izhevskoye, he lost most of his hearing at age 10 after a bout of scarlet fever. The deafness isolated him socially, but drove him inward, into books, into thought experiments, into a private world of ideas that turned out to be decades ahead of their time. He was largely self-taught. He couldn't attend regular school because of his hearing, so he spent years reading everything he could find in libraries, teaching himself physics, mathematics, and astronomy. By the 1890s, Tsiolkovsky was working as a provincial schoolteacher, living modestly, and spending his evenings doing calculations that would lay the theoretical foundation for all of spaceflight. In 1903, the same year the Wright brothers made their first powered flight at Kitty Hawk, he published a paper called Exploration of Outer Space by Means of Rocket Devices. And in that paper, he derived something now known as the Tsiolkovsky rocket equation. It's one of the most important equations in aerospace engineering, and it describes a relationship that every rocket designer in history has had to wrestle with. Here's what it says, in plain terms. The speed a rocket can ultimately reach depends on two things: how fast the exhaust gases leave the engine, and the ratio of the rocket's total mass, fully fueled, to its mass when the fuel is all burned. That ratio is everything, and here's why it's such a brutal constraint. Rocket fuel is heavy, really heavy. If you want to go faster, you need more fuel. But more fuel means more weight, which means you need even more fuel to lift that extra fuel. It's a vicious circle, and it means that for any given type of propellant, there's a practical limit to how fast you can go. Tsiolkovsky understood this deeply, and he proposed solutions that wouldn't be implemented for decades: liquid-fueled rockets, multi-stage rockets where you throw away empty fuel tanks as you go to reduce weight, even the idea of space stations and airlocks. Think about what that means. A deaf schoolteacher in rural Russia, working alone with pencil and paper, figured out the basic architecture of space travel before anyone had even built an airplane that could stay aloft for more than a few seconds. He described multi-stage rockets 60 years before the Saturn V. He wrote about space stations 70 years before Salyut 1. He even speculated about settling other planets. And almost nobody noticed. His papers were published in obscure Russian journals, read by almost no one outside a small circle. He lived in near poverty for most of his life, and it wasn't until the Soviet Union later adopted him as a national hero of science that his contributions were widely recognized. But Tsiolkovsky was a theorist. He never built a rocket. He never tested an engine. He gave the world the math, the vision, the theoretical roadmap. Turning that roadmap into reality, into actual fire and metal and thrust that would fall to other people, in other countries, working under very different circumstances. And the first person to truly bridge that gap between theory and hardware, the person who actually built and flew the world's first liquid-fueled rocket, was an American physics professor with a workshop in his aunt's farm in Auburn, Massachusetts. His name was Robert Goddard, and the story of what happened on March 16, 1926, on that frozen New England field, is one of those moments where the future quietly arrives and almost nobody notices. The rocket was tiny. Laughably small, really. If you saw a picture of it, you might mistake it for a piece of plumbing someone had welded together in their garage, which honestly isn't that far from the truth. It stood about 10 feet tall, held together by a frame that looked like it belonged on a coat rack, and the engine, the actual combustion chamber, sat at the top, not the bottom, because Goddard believed at the time that pulling the rocket from above would be more stable than pushing it from below. He was wrong about that, as it turned out, but the basic principle worked. The fuel was gasoline. The oxidizer was liquid oxygen. And on that cold March afternoon, with his wife Esther and a couple of colleagues watching from a safe distance, well, a hopefully safe distance, Goddard lit the engine using a blowtorch attached to a long pole, and the rocket rose into the air. It flew for about 2.5 seconds. It reached an altitude of roughly 41 feet. It traveled a horizontal distance of maybe 184 feet before crashing into a frozen cabbage field. And that was it. That was the entire flight. 2.5 seconds of powered, liquid-fueled rocketry, and then silence. But here's the thing. Those 2.5 seconds changed everything. Because what Goddard had just demonstrated was that Tsiolkovsky's theory actually worked in practice. You could burn liquid fuel and liquid oxidizer together in a controlled combustion chamber, direct the exhaust through a nozzle, and generate enough thrust to lift a vehicle off the ground. It sounds obvious now, but in 1926, a lot of very smart people genuinely believed that rockets couldn't work in a vacuum, that there was nothing to push against in space, so the whole idea was fundamentally flawed. A New York Times editorial had actually mocked Goddard for suggesting rockets could work beyond the atmosphere, saying he lacked the knowledge ladled out daily in high schools. They said he didn't understand Newton's third law, which is ironic because Newton's third law, every action has an equal and opposite reaction, is precisely why rockets do work in a vacuum. The exhaust pushes one way, the rocket goes the other. You don't need air to push against. You're pushing against your own exhaust. Goddard understood this perfectly. The New York Times didn't issue a correction until 1969, the day after Apollo 11 launched, 43 years later. But Goddard wasn't just right about the physics. He was decades ahead on the engineering too. Over the next 15 years or so, working mostly in isolation in Roswell, New Mexico, yes, that Roswell, long before it became famous for other reasons, Goddard built increasingly sophisticated rockets. He developed gyroscopic stabilization systems to keep his rockets flying straight. He invented vane-based thrust vectoring, using small deflectors in the exhaust stream to steer the rocket. He experimented with fuel pumps, with different nozzle designs, with ways to cool the combustion chamber so it wouldn't melt. By the mid-1930s, his rockets were reaching altitudes of over a mile. He filed more than 200 patents, and almost nobody in the American scientific establishment took him seriously. This is one of those painful threads that runs through early rocketry. The people who were right, who saw the future most clearly, were almost always dismissed, underfunded, or outright ridiculed. Goddard was intensely private, partly by temperament, and partly because he'd been burned by that New York Times mockery, and by the general attitude that rockets were the stuff of science fiction, not serious science. He didn't publish much. He didn't collaborate widely. He worked with a small team, funded partly by the Smithsonian Institution and later by grants arranged through Charles Lindbergh, who visited Goddard's workshop and immediately recognized the significance of what he was doing. But the U.S. military showed almost no interest. The Army, the Navy, they came, they looked, they shrugged. Rockets seemed impractical, unreliable, dangerous, which, to be fair, they were. But that was the whole point of the research, to make them less so. And while Goddard was working in relative obscurity in the New Mexico desert, something very different was happening in Germany. Because the Germans were paying attention. They were paying very close attention. Let's talk about Hermann Oberth for a moment. Oberth was a Romanian-born German physicist who, independently of Tsiolkovsky and roughly contemporaneously with Goddard, had worked out much of the same theory. His 1923 book, Die Rakete zu den Planetenräumen, The Rocket into Planetary Space, laid out the mathematics of spaceflight in rigorous detail. Unlike Tsiolkovsky's work, which had been buried in obscure Russian journals, Oberth's book was published in German, which was one of the dominant scientific languages of the era, and it found an audience. It inspired a generation of young German engineers and enthusiasts who formed rocket clubs, built small experimental rockets, and dreamed of space travel with an intensity that bordered on obsession. The most important of these clubs was the Verein für Raumschifffahrt, the Society for Space Travel, founded in 1927. And among its youngest and most enthusiastic members was a teenager named Wernher von Braun. Von Braun came from an aristocratic Prussian family. His mother gave him a telescope when he was confirmed in the Lutheran Church, and from that point on, he was consumed by the idea of reaching space. He was terrible at math as a young student, but when he realized that math was the language of rocketry, he attacked it with ferocious determination and became excellent. He joined the Rocket Society, he worked with Oberth on experiments, and by his early 20s, he was one of the most talented rocket engineers in Germany. And here's where the story takes a darker turn, because you can't tell the history of rocketry without confronting the fact that the technology was developed in its most dramatic early form, not for exploration, but for war. The German army had been watching the amateur rocket societies with interest, and for a very specific reason. The Treaty of Versailles, which ended World War I, had imposed strict limits on German artillery, the range and caliber of guns they could build. But the treaty said nothing about rockets, because in 1919, nobody thought rockets were weapons. So the German military saw an opportunity. If they couldn't build bigger guns, maybe they could build guided rockets instead. And they recruited von Braun. In 1932, von Braun began working for the German Army's Ordnance Department. By 1937, the operation had moved to a remote facility on the Baltic coast called Peenemünde, and von Braun was its technical director. He was 25 years old, and over the next several years, with essentially unlimited funding and thousands of engineers and workers at his disposal, von Braun's team built the A4 rocket, better known by its propaganda name, the V2. The V2 is one of those engineering achievements that forces you to hold two completely contradictory thoughts in your head at the same time. On one hand, it was a genuine marvel. It was the world's first long-range guided ballistic missile, and the first human-made object to reach the boundary of space. It stood about 46 feet tall, weighed nearly 28,000 pounds fully fueled, and was powered by a liquid fuel engine burning ethanol and liquid oxygen that produced around 56,000 pounds of thrust. It used an inertial guidance system with gyroscopes and accelerometers to navigate. It could reach an altitude of roughly 55 miles, well above the Kármán line that we now use to define the edge of space, and travel about 200 miles downrange at speeds exceeding 3,000 miles per hour. When it re-entered the atmosphere, it was moving faster than the speed of sound, which meant you couldn't hear it coming. There was no defense against it. There was no warning, just sudden, devastating impact. And that's the other hand, because the V2 was a weapon of terror. Beginning in September 1944, Germany launched more than 3,000 V2s at targets in England, Belgium, and France. They killed an estimated 9,000 people, mostly civilians, and the production of the rockets was arguably even more horrific than their use. The V2s were assembled in an underground factory called the Mittelwerk, carved into a mountain near Nordhausen, using forced labor from the Mittelbau-Dora concentration camp. The conditions were nightmarish. Prisoners worked in tunnels with almost no ventilation, little food, rampant disease, An estimated 20,000 people died in the production of the V-2. More people died building the rocket than were killed by it. And von Braun knew. The degree of his personal involvement and moral responsibility has been debated for decades, but he held the rank of SS officer, he visited the Mittelwerk, and there is documentation that he was aware of the conditions. After the war, he would spend the rest of his life insisting that he had been interested only in space travel, that the military application was something he tolerated as a means to an end. "I aimed for the stars," he reportedly said, to which the satirist Mort Sahl added, "But sometimes I hit London." It's a complicated legacy, to say the least. Von Braun was brilliant, charismatic, visionary, and deeply compromised. And the moral complexity of his story is inseparable from the history of space exploration itself, because without the V-2, the trajectory of rocketry and everything that followed would have been fundamentally different. When the war ended in 1945, the V-2 became the most sought-after piece of technology on the planet. Both the Americans and the Soviets understood immediately that whoever controlled this technology would control the future of long-range weaponry and potentially access to space. What followed was essentially a scramble, a frantic, sometimes chaotic race to grab as many rockets, as many documents, and as many German rocket scientists as possible before the other side could get to them. The American effort was called Operation Paperclip. In the final weeks of the war, von Braun and about 120 of his top engineers surrendered to American forces, deliberately, because they calculated that their prospects were better with the Americans than with the Soviets. The U.S. Army shipped them to the United States along with enough V-2 components to assemble roughly 80 complete rockets. Von Braun and his team were initially set up at Fort Bliss in Texas and the White Sands Proving Ground in New Mexico, where they spent the late 1940s launching captured V-2s, training American engineers, and essentially teaching the United States how to build large rockets. The Soviets, meanwhile, conducted their own operation. They captured the Mittelwerk factory, seized whatever V-2 hardware and documentation remained, and recruited, sometimes voluntarily, sometimes not, a number of German engineers who hadn't made it west. But the Soviet rocket program would ultimately be driven not by captured Germans, but by a homegrown genius, a man whose identity was kept so secret that for decades the Western world knew him only as the chief designer. His real name was Sergei Korolev, and his story is, if anything, even more remarkable than von Braun's, and far more harrowing. Because before Korolev became the architect of the Soviet space program, before he launched the first satellite and the first human into orbit, he spent 6 years in the Soviet Gulag system, including time in a gold mine in Kolyma, one of the most brutal labor camps in human history. Kolyma, in the far northeast of Siberia, where winter temperatures dropped to -50 degrees Celsius, where prisoners were worked to exhaustion mining gold in frozen earth, where the death rate was staggering. Korolev was sent there in 1938 during Stalin's Great Purge, convicted on fabricated charges of sabotage and treason. He was 31 years old. And here's what you need to understand about who Korolev was before the Gulag, because it makes everything that came after almost impossible to believe. He was already a brilliant rocket engineer. He'd been obsessed with spaceflight since his 20s, had helped found one of the Soviet Union's earliest rocket research groups, GERD, the Group for the Study of Reactive Motion, in Moscow in the early 1930s. By 1933, his team had launched the first Soviet liquid-fueled rocket. He was doing serious, real work, the kind of work that should have made him a national hero. Instead, during the paranoid frenzy of the purges, Someone, possibly a professional rival, possibly just a frightened colleague trying to save himself, denounced Korolev. That was all it took. He was arrested, interrogated, beaten so badly that his jaw was broken, convicted in a sham trial, and sentenced to 10 years of hard labor. First he was sent to a transit camp, then to Kolyma. Think about that for a moment. A man with the knowledge and vision to open the door to space, digging for gold in a Siberian death camp. He nearly died there. He contracted scurvy. He lost most of his teeth. He was malnourished to the point of heart damage that would affect him for the rest of his life. And yet somehow, through a combination of luck and the intervention of other imprisoned scientists who recognized his talent, Korolev was eventually transferred out of Kolyma. He was moved to a Sharashka, one of those peculiar Soviet institutions, a prison laboratory where jailed engineers and scientists were put to work on military projects. Still a prisoner, still under guard, but at least working on aircraft and rocket design instead of dying in a mine. He spent the rest of the war years in these prison design bureaus, contributing to the Soviet war effort while technically remaining a convict. He wasn't fully released until 1944, and even then his record wasn't cleared. He carried that conviction with him. And yet, within just a few years, this man, this former Gulag prisoner with broken health and a criminal record, became the most important figure in the Soviet space program. The state that had nearly killed him handed him the keys to its most ambitious technological project. If you wrote this as fiction, nobody would believe it. Now, here's where Korolev's path intersects with what the Soviets had captured from Germany. In 1945 and 1946, Korolev traveled to Germany to study the V2 firsthand. He was deeply impressed. The V2 was far more advanced than anything the Soviets had built. But he also saw its limitations clearly. He understood that simply copying the V2 wasn't enough. You had to understand the principles, absorb the engineering philosophy, and then go beyond it. And that's exactly what he did. The Soviets did build their own version of the V2, called the R1, which was essentially a direct copy. But Korolev was already thinking bigger. He was thinking about rockets powerful enough to reach orbit, rockets that could carry payloads across continents, rockets that could, someday, carry people into space. And this is where the story splits into two parallel tracks that would define the next decade. On one side, you have von Braun in America, a public figure with a charming accent and a gift for selling the dream of space to the American public, appearing on television, consulting with Walt Disney, publishing articles in Collier's magazine with gorgeous illustrations of space stations and moon missions. On the other side, you have Korolev in the Soviet Union, a man whose very name was classified, who couldn't publish under his own identity, who was referred to only as the chief designer in any public communication, whose face was unknown to the outside world. Two men, both driven by the same fundamental dream, getting humanity into space, working on opposite sides of an ideological divide, each constrained and enabled by the political system they lived under. But here's the thing. In the early 1950s, neither of them was primarily building rockets for space exploration. They were building weapons. The driving force behind the massive investment in rocket technology, on both sides, was the need to deliver nuclear warheads over intercontinental distances. The Cold War had created a terrifying logic. If your enemy has nuclear bombs, you need a way to deliver them to their cities before they can deliver theirs to yours. Bombers could be shot down, but a ballistic missile, screaming in from the edge of space at thousands of miles per hour, that was essentially unstoppable with 1950s technology. So both superpowers poured enormous resources into building intercontinental ballistic missiles, ICBMs, and the people who knew the most about large rockets, von Braun and Korolev, suddenly found themselves with budgets and support they could never have dreamed of. Korolev, in particular, benefited from a peculiar technical circumstance. Soviet nuclear weapons in the early 1950s were heavier than American ones. The Soviets hadn't yet mastered the miniaturization techniques that allowed the Americans to build relatively compact warheads. So Korolev's ICBM had to be powerful enough to loft a very heavy payload, on the order of 5 tons or more, across intercontinental range. This meant he needed to build a truly enormous rocket, and the rocket he designed, the R-7, was a masterpiece of engineering that would change history in ways nobody at the Kremlin fully anticipated. The R-7, and let's talk about this rocket for a minute because it deserves it. Korolev's design used a cluster of engines rather than a single massive one. The core stage was surrounded by 4 strap-on boosters, each with its own set of engines, all burning kerosene and liquid oxygen. At liftoff, all the engines fired simultaneously, producing roughly 400 tons of thrust. The 4 boosters would burn out and fall away about 2 minutes into flight, and the core stage would continue to accelerate the payload to orbital velocity. This staging concept, shedding mass as you go, was pure Tsiolkovsky, the fundamental insight from that 1903 paper we talked about earlier, now realized in steel and fire. The total height of the R-7 was about 30 meters, and it weighed nearly 300 tons fully fueled. It was, by a significant margin, the most powerful rocket in the world when it first flew, and it first flew in 1957. The initial test launches were rocky. The first attempt in May 1957 failed when one of the strap-on boosters caught fire and the rocket broke apart. But by August, they had a successful flight. The R-7 traveled its full intercontinental range, and the Soviet Union officially had a weapon that could strike the American homeland. But Korolev had been planning for something else all along. He had been quietly lobbying the Soviet leadership for permission to use the R-7 not just as a weapon, but as a space launch vehicle. And because the R-7 was so powerful, because it had been designed to carry those heavy Soviet warheads, it had more than enough capability to put a small payload into orbit around the Earth. On October 4th, 1957, a modified R-7 launched from the Baikonur Cosmodrome in the desert steppes of Kazakhstan, carrying a polished aluminum sphere 58 centimeters in diameter, weighing about 83 kilograms. It had 4 trailing antennas and a simple radio transmitter that broadcast a steady beep-beep-beep on frequencies that any amateur radio operator in the world could pick up. They called it Sputnik. The word means traveling companion in Russian. And when it reached orbit, everything changed. Everything. It's hard to overstate the psychological impact. Americans could go outside at dusk, look up, and see this tiny point of light moving steadily across the sky. A Soviet-made object, circling the Earth every 96 minutes, passing over their homes, their cities, their military bases, and there was absolutely nothing they could do about it. The beeping signal was picked up by radio stations around the world and broadcast on the news. It was the sound of the future arriving, and for the United States, it was a profound shock. If the Soviets could put a satellite in orbit, they could put a nuclear warhead anywhere on the planet. The technology was essentially the same. Sputnik was a propaganda triumph of the highest order, and it triggered what we now call the space race in earnest. The American response was, initially, embarrassing. The U.S. had its own satellite program, Project Vanguard, run by the Naval Research Laboratory, but it wasn't ready. Under enormous political pressure to respond to Sputnik, they rushed a Vanguard rocket to the launch pad in December 1957, It rose about 4 feet off the pad, lost thrust, settled back down, and exploded in a spectacular fireball on live television. The press called it Flopnik and Kaputnik. It was a national humiliation. And this is where von Braun finally got his chance. He and his team at the Army Ballistic Missile Agency in Huntsville, Alabama, had been developing their own rocket, the Jupiter C, and von Braun had been arguing for months that he could put a satellite in orbit if they just let him try. After the Vanguard disaster, the government finally said yes. On January 31st, 1958, a Jupiter C rocket, which was really a modified Redstone missile, itself a direct descendant of the V-2, launched Explorer-1, America's first satellite, into orbit. And Explorer-1 wasn't just a beeping sphere. It carried a cosmic ray detector designed by physicist James Van Allen, and that instrument made a genuine scientific discovery. It detected the belts of charged particles trapped by Earth's magnetic field, which we now call the Van Allen radiation belts. So America's first satellite actually did science, which was a nice counterpoint to the Soviet achievement. But the Soviets weren't done. Not even close. Korolev kept pushing, kept launching, kept achieving firsts. In November 1957, just a month after Sputnik, he launched Sputnik 2, which carried the first living creature into orbit, a stray dog named Laika, pulled from the streets of Moscow. And here, we should be honest about what happened. Laika's mission was one way. There was no plan to bring her back. The technology to deorbit and recover a spacecraft didn't exist yet. The official Soviet story for decades was that Laika survived for about a week before being painlessly euthanized by poisoned food. The truth, which didn't come out until 2002, was that Laika died within hours of reaching orbit, probably from overheating and stress. It's a reminder that the space race, for all its wonder, had real costs, not just in money and risk, but in the lives of creatures who had no say in the matter. The pace of events in the late 1950s was extraordinary. In 1958, the United States created NASA, the National Aeronautics and Space Administration, consolidating its various space efforts under a single civilian agency. This was a deliberate choice. Space exploration would be, officially at least, a peaceful scientific endeavor, not purely a military one. Meanwhile, both sides were working furiously on the next great challenge, not just putting objects in orbit, but bringing them back safely and eventually putting humans up there. Korolev was already designing the spacecraft that would do exactly that. He called it Vostok, which means east in Russian, and its design was elegant in its simplicity. The capsule was a sphere, the most straightforward shape for surviving re-entry, because a sphere's aerodynamic properties are the same regardless of its orientation. You don't have to worry about it tumbling or entering the atmosphere at the wrong angle. The heat shield covered the entire surface. Inside, there was room for one cosmonaut, life support systems, and enough supplies for about 10 days in orbit, though the planned missions were much shorter. The cosmonaut would ride inside during launch and orbit, and then, and this is a detail that the Soviets kept secret for years, during the final phase of descent, after the capsule had slowed enough in the atmosphere, the cosmonaut would eject from the capsule and parachute down separately, because the Vostok capsule's landing was too rough for a human to survive inside it. The capsule came down under its own parachute, but it hit the ground hard. Before they put a person in it, they tested the system with dogs, pairs of dogs, this time with the intention of bringing them back alive. In August 1960, Vostok prototype Korabl Sputnik 2 carried 2 dogs named Belka and Strelka into orbit, along with a rabbit, 42 mice, 2 rats, and some fruit flies. They all came back alive. It was the first successful recovery of living creatures from orbit, and it proved the concept. The path to human spaceflight was open, and the person Korolev chose to walk that path, or rather, to ride it, was a 27-year-old fighter pilot from a small town west of Moscow, a man with an infectious grin and a calm demeanor that impressed everyone who met him. His name was Yuri Gagarin, and on the morning of April 12, 1961, he climbed into the Vostok 1 capsule atop a modified R-7 rocket at Baikonur. The rocket that Korolev had originally designed to carry nuclear warheads was about to carry a human being into orbit for the first time in history. Gagarin reportedly said, "Poyakali," as the engines ignited. "Let's go." And in 108 minutes, he completed a single orbit of the Earth, traveling at nearly 28,000 kilometers per hour, seeing what no human had ever seen: the full curve of the planet, the thin blue line of the atmosphere, the blackness of space beyond. The re-entry was not entirely smooth. The service module failed to separate cleanly from the capsule, and the joined spacecraft tumbled wildly for about 10 minutes before the connecting straps finally burned through in the heat of re-entry and the capsule stabilized. Gagarin ejected at about 7 kilometers altitude and parachuted to a field near the Volga River, where he was found by a farmer and her granddaughter, who were initially startled by the orange-clad figure descending from the sky. He told them not to be afraid, that he was a Soviet citizen who had come from space. And just like that, the space race had a new scoreboard, and the Soviets were winning by a wide margin. First satellite, first animal in orbit, first human in orbit. The United States was reeling, and a young president named John F. Kennedy was about to make a decision that would reshape the entire trajectory of space exploration, a decision driven not primarily by science or curiosity, but by Cold War politics, national pride, and the desperate need to find a goal so audacious that the Soviets couldn't get there first. Kennedy needed a finish line, and the one he chose was the moon. On May 25, 1961, barely 6 weeks after Gagarin's flight, Kennedy stood before a joint session of Congress and delivered the line that would define a decade of engineering ambition. "I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth." And here's the thing. When Kennedy said those words, the United States had exactly 15 minutes of human spaceflight experience. That's it. Alan Shepard had flown his Mercury capsule on a suborbital arc just 3 weeks earlier, on May 5th. He went up, he came down, he spent about 15 minutes in the air, and he never even reached orbit. And now the president was standing in front of Congress saying, essentially, we're going to send people 250,000 miles away, land them on another world, and bring them home in less than 9 years. Think about what that means from an engineering perspective. In 1961, nobody knew how to rendezvous 2 spacecraft in orbit. Nobody knew how to build a rocket powerful enough to send a crewed vehicle to the moon. Nobody knew whether a human being could survive a week in space, let alone perform complex tasks in a spacesuit on the lunar surface. Nobody even knew for certain what the surface of the moon was like. There was a genuine concern among some scientists that the lunar soil might be so fine and powdery that a spacecraft would simply sink into it like quicksand. The engineering problems that needed to be solved were not incremental improvements on existing technology. They were problems that hadn't been solved because nobody had ever needed to solve them before, and Kennedy was putting a deadline on it. But that's what made it brilliant. Strategically, Kennedy and his advisors, particularly Vice President Lyndon Johnson, had consulted with NASA leadership, with Von Braun, with others, and the question they asked wasn't, What's the next logical step in space? The question was, what can we do that we have a chance of beating the Soviets at? Low Earth orbit? The Soviets were already there. A space station? The Soviets could probably do that sooner. But the moon was so far beyond what anyone had done that it reset the race. It was a goal so enormous that the Soviets' existing lead wouldn't matter as much. Both nations would essentially be starting from scratch, and the United States, with its vastly larger economy and industrial base, might actually have an advantage in a long-distance race rather than a sprint. Now, NASA had to figure out how to actually do this. And the first major engineering decision, one that shaped absolutely everything that followed, was the question of mission architecture. How do you actually get people to the moon and back? There were three main approaches debated. The first was called direct ascent. You build one enormous rocket, you fly it straight to the moon, you land the whole thing on the lunar surface, and then you launch it back off the moon and fly home. Simple in concept, staggering in execution. This would have required a rocket called Nova, even bigger than what eventually became the Saturn V, and the engineering challenges of landing that much mass on the moon and then launching it again were immense. The second approach was Earth Orbit Rendezvous. You launch multiple rockets into Earth orbit, assemble or refuel a moon-bound spacecraft up there, and then send it on its way. This had the advantage of using smaller individual rockets, but it required solving the problem of orbital rendezvous and docking, something nobody had done yet. And it meant multiple launches for every moon mission, with all the complexity and timing headaches that implied. The third option was the one that won, and it was championed primarily by a NASA engineer named John Houbolt. It was called Lunar Orbit Rendezvous, and when Houbolt first proposed it, a lot of people thought it was crazy. Here's how it works. You launch everything on one big rocket, but instead of taking the whole spacecraft down to the moon's surface, you leave the main ship, the command and service module, in orbit around the moon with one astronaut aboard. A smaller, lighter, purpose-built landing craft, the lunar module, detaches, carries two astronauts down to the surface, and then launches just its upper stage back up to rendezvous with the orbiting command module. The crew transfers back, they jettison the lunar module, and they fly home in the command module. Now, you might be thinking, that sounds more complicated, not less. And in terms of the number of steps, yes, it is. You've got separation, descent, ascent, rendezvous, docking, all happening around the moon, about 240,000 miles from any help. If the rendezvous fails, the two astronauts in the lunar module are stranded in lunar orbit with no way home. The risk is real. But here's what's really clever about it. By not taking the entire spacecraft down to the surface, you drastically reduce the mass that needs to land on the moon and launch off it again. The lunar module could be small and light, built for just 2 people, with thin walls, designed to operate only in the vacuum of space and the moon's weak gravity. It didn't need a heat shield because it was never coming back to Earth. It didn't need to be aerodynamic because there's no air on the moon. Every kilogram you save on the lander is a kilogram you don't have to launch off the lunar surface, which means less fuel, which means less mass, which means less fuel again. That tyranny of the rocket equation that Tsiolkovsky described back in 1903, working in your favor for once instead of against you. Houbolt actually went over the heads of his superiors to make his case, writing directly to the Associate Administrator of NASA, because he felt so strongly that this was the right approach and that the bureaucracy was going to kill it. He was right. Lunar Orbit Rendezvous made the whole mission possible with a single launch vehicle, the Saturn V, instead of requiring something even more gargantuan or multiple launches. And the Saturn V. Let's talk about the Saturn V for a moment, because this rocket is one of the most extraordinary machines ever built. Von Braun and his team at the Marshall Space Flight Center in Huntsville, Alabama, designed it, and it remains to this day the most powerful rocket ever successfully flown. It stood 363 feet tall, taller than the Statue of Liberty. Fully fueled, it weighed about 6.5 million pounds. Its first stage, the SIC, was powered by 5 F1 engines, each one producing 1.5 million pounds of thrust. 5 of them together generated 7.5 million pounds of thrust at liftoff. The sound alone was something people described as not just heard, but felt in the chest from miles away. Each F1 engine burned about 3 tons of kerosene and liquid oxygen per second. Per second. The turbopump that fed propellant into each engine generated more horsepower than all the engines on a Navy destroyer combined. And here's a detail that gives you a sense of the engineering precision involved: the combustion instability problem. When you're burning that much propellant that fast in a single combustion chamber, you get pressure oscillations, waves of high and low pressure bouncing around inside the chamber, and if those oscillations reinforce each other, they can tear the engine apart in milliseconds. The F1 engineers struggled with this for years. Engines would explode on the test stand with no warning. The solution they eventually found was partly empirical. They would deliberately set off small bombs inside the combustion chamber during testing to create instability, and then modify the injector plate design until the engine could damp out those oscillations and recover. They tested and modified, hundreds of times, until they had an injector pattern that was inherently stable. It was engineering by persistence as much as by theory. The second stage, the S2, used 5 J2 engines burning liquid hydrogen and liquid oxygen, a much more efficient propellant combination, but also much harder to handle, because liquid hydrogen has to be kept at -253 degrees Celsius. The third stage, the S4B, had a single J2 engine, and was the stage that actually performed the translunar injection burn, the push that sent the spacecraft out of Earth orbit and on its way to the Moon. But while the Saturn V was being developed, NASA had an entire program to run first. The Gemini program, which flew between 1965 and 1966, and which was essentially a crash course in all the skills astronauts would need for a lunar mission. Gemini was where NASA learned to do spacewalks, to rendezvous and dock 2 spacecraft, to stay in space for up to 2 weeks. Ed White performed the first American spacewalk on Gemini 4 in June 1965, and he enjoyed it so much that he had to be ordered back inside the capsule. Gemini 6 and 7 performed the first true space rendezvous in December 1965, with the 2 spacecraft flying in formation just a foot apart, and Gemini 8, flown by Neil Armstrong and David Scott in March 1966, achieved the first docking with another spacecraft, an unmanned Agena target vehicle, but then nearly ended in disaster when a stuck thruster on the Gemini capsule sent the docked spacecraft into an increasingly violent spin. Armstrong undocked, which actually made the spin worse because the Gemini was lighter without the Agena, and the stuck thruster spun it even faster, nearly 1 revolution per second. Armstrong had to shut down the main maneuvering system entirely and use the re-entry thrusters to stabilize the spacecraft, which meant the mission had to be cut short. But his calm under pressure in that moment was noted. It was one of the reasons he would eventually be chosen to command Apollo 11. Meanwhile, the Soviets were not standing still. Korolev was working on his own lunar program, developing a massive rocket called the N-1, which was in some ways even more ambitious than the Saturn V. But Korolev was fighting bureaucratic battles, competing with rival designers like Vladimir Chelomey and Valentin Glushko for resources and political support. And then, on January 14, 1966, Korolev went into surgery for what was supposed to be a routine operation to remove intestinal polyps. He was only 59, but his body had never fully recovered from the years in the Gulag, the broken jaw, the damaged heart, the scurvy. During the surgery, the doctors discovered a large tumor and complications arose. Sergei Korolev, the chief designer, the man who had launched Sputnik, who had sent Gagarin into orbit, who had been the driving force behind the entire Soviet space program, died on the operating table. The Soviet program lost its most brilliant and forceful leader at the worst possible moment, and the consequences of that loss would ripple through everything that followed. The N-1 rocket, without Korolev's guiding hand, would go on to fail spectacularly. 4 launches, 4 failures, including one that produced one of the largest non-nuclear explosions in history when the rocket fell back onto the launch pad. But that's getting ahead of ourselves, because back in the United States, the Apollo program was about to face its own darkest moment, and it happened not in space, but on the ground, inside a spacecraft that hadn't even left the launch pad. On January 27, 1967, the crew of Apollo 1, Gus Grissom, Ed White, and Roger Chaffee, were conducting a routine launch rehearsal test inside their command module, which was pressurized with pure oxygen at slightly above atmospheric pressure. A spark from damaged wiring ignited something inside the cabin, and in that pure oxygen environment, the fire spread with terrifying speed. The crew couldn't open the hatch. It was a plug door that opened inward, held shut by the internal pressure, and even under normal conditions it took about 90 seconds to open. In a cabin filling with flame and toxic smoke, 90 seconds was an eternity. All 3 astronauts died. The investigation that followed found sloppy wiring, flammable materials throughout the cabin, and a hatch design that was essentially a death trap in a fire scenario. NASA had been moving so fast, under so much pressure to meet Kennedy's deadline, that safety had been compromised in ways that were, in hindsight, inexcusable. The fire forced a painful 18-month pause in crewed Apollo flights. The command module was redesigned extensively. A new quick-opening outward-swinging hatch, a switch from pure oxygen at high pressure to a mixed nitrogen-oxygen atmosphere at launch, removal of flammable materials, improved wiring. The redesigned Block 2 command module was a fundamentally safer spacecraft, and many engineers later said that without the fire and the redesign it forced, Apollo might never have made it to the moon successfully. That's a hard thing to say, knowing 3 men died, but it reflects a brutal truth about engineering. Sometimes the lessons that save the most lives are learned at the highest cost. And it was in this atmosphere of grief and renewed determination that NASA pressed forward, testing the Saturn V for the first time in an unmanned flight in November 1967. Then, accelerating through a series of increasingly ambitious missions. Apollo 7 tested the redesigned command module in Earth orbit. Apollo 8, in December 1968, did something breathtaking. It sent Frank Borman, Jim Lovell, and Bill Anders all the way to the moon and back, orbiting the moon 10 times on Christmas Eve. They became the first humans to see the far side of the moon with their own eyes, and Anders took that famous photograph, Earthrise, showing our planet rising above the lunar horizon, small and blue, and impossibly fragile against the blackness. That image changed how people thought about Earth itself. Apollo 9 tested the lunar module in Earth orbit. Apollo 10 was essentially a full dress rehearsal, taking the lunar module down to within about 50,000 feet of the lunar surface before pulling back and returning to lunar orbit. Tom Stafford and Gene Cernan flew that lunar module so close they could see boulders, craters, the actual terrain where a landing might happen. And then they came home. Everything worked. The hardware was ready. The procedures were proven. The only thing left was to actually do it. So let's talk about Apollo 11. July 16th, 1969. Cape Kennedy, Florida. The morning is warm and hazy, and there's a Saturn V standing on pad 39A, fully fueled, ticking and creaking as super-cold propellants boil off in the summer heat. Inside the command module Columbia, 3 men are strapped into their couches. Neil Armstrong, commander, on the left, Michael Collins, command module pilot, in the center, and Buzz Aldrin, lunar module pilot, on the right. About 1 million people have gathered along the beaches and causeways nearby to watch. Millions more are watching on television around the world. At 9:32 in the morning Eastern Time, those 5 F1 engines ignite, and the Saturn V lifts off. You already know how powerful this thing is. 7.5 million pounds of thrust, the most powerful rocket ever successfully flown. The first stage burns for about 2.5 minutes, pushing the vehicle to around 38 miles altitude and about 6,000 miles per hour before it separates and falls away into the Atlantic. The S-2 second stage takes over, its 5 J-2 engines burning liquid hydrogen and liquid oxygen, and after about 6 minutes, that stage separates too. The S-4B third stage fires briefly to reach Earth orbit, and then the crew spends about 2.5 hours checking systems before the SIVB fires again for translunar injection, the burn that sends them on a trajectory toward the moon. That's a roughly 3-day coast. Now here's something worth sitting with. During that coast, the spacecraft is getting farther from Earth than any human being has ever been, except for the crews of Apollo 8 and 10. The Earth is shrinking behind them. The moon is growing ahead. And inside that little command module, which is about the interior volume of a large car, 3 people are living, eating, sleeping, navigating, and trying to stay calm about what they're about to attempt. Something no one has ever done. On July 19th, they fire the Service Propulsion System engine to enter lunar orbit. They spend a day orbiting, checking systems, studying the landing site through the windows, and then on July 20th, Armstrong and Aldrin crawl through the tunnel into the lunar module Eagle, seal the hatch, separate from Columbia, and begin their descent. Collins stays behind, orbiting alone, the loneliest person in the solar system. Every time he passes behind the moon, he's cut off from all radio contact with both his crewmates and the entire Earth. The descent is where things get tense. The lunar module's guidance computer is running a program called P64, transitioning to P66 for the final approach. And during the descent, the computer starts throwing alarms. Program alarm 1202, then 1201. These are executive overflow alarms. The computer is being asked to do more tasks than it can handle simultaneously. In Mission Control, a 26-year-old guidance officer named Steve Bales has about seconds to decide whether to call an abort. He'd studied these alarms. He knew that as long as they weren't continuous, the computer was shedding lower priority tasks and keeping the critical ones running. He calls go. Flight Director Gene Kranz relays the go. The descent continues. But there's another problem. Armstrong looks out the window and sees that the autopilot is taking them toward a boulder field at the edge of a large crater. West Crater, it's called. Not a good place to land. So he takes semi-manual control, flying the lunar module forward, skimming over the boulders, looking for a clear spot. Fuel is running low. In mission control, Charlie Duke is calling out the remaining propellant. 60 seconds of fuel, then 30 seconds. At 30 seconds, they're moments from a mandatory abort. And then Aldrin calls out, "Contact light." A probe dangling below one of the landing pads has touched the surface. Armstrong shuts down the engine. The Eagle settles onto the moon with somewhere between 15 and 25 seconds of fuel remaining, depending on which estimate you trust. "Houston, Tranquility Base here. The Eagle has landed." And Charlie Duke, his voice cracking, replies, "Roger, Tranquility, we copy you on the ground. You got a bunch of guys about to turn blue. We're breathing again." Think about what just happened from an engineering standpoint. A vehicle designed and built by hundreds of thousands of people, launched from Florida on a pillar of fire, coasted for 3 days across 250,000 miles of vacuum, entered orbit around another world, separated into 2 pieces, and landed on the surface of the moon with human beings inside. Every system had to work. The guidance computer, the radar, the descent engine, which, by the way, was throttleable, one of the first throttleable rocket engines ever built, designed by the team at TRW. The reaction control thrusters, the life support, the communications. Thousands of components, millions of parts, and the whole thing came down to a test pilot hand-flying the last few hundred feet because the terrain wasn't what they expected. About 6.5 hours after landing, Armstrong opens the hatch and begins climbing down the ladder. It's July 20th, 1969, 10:56 p.m. Eastern Time. He steps off the footpad and says those words. That's one small step for man, one giant leap for mankind. He later said he intended to say a man, and some audio analysis supports that the A might be there, just lost in the transmission. Either way, it's one of the most famous sentences in human history. Aldrin joins him about 20 minutes later. They spend roughly 2.25 hours on the surface. They plant a flag, collect about 47 pounds of lunar samples, deploy a few scientific instruments, a seismometer, a laser-ranging retroreflector that scientists still bounce lasers off of today to measure the Earth-Moon distance to within centimeters. They take photographs. They talk to President Nixon on the phone. And then they climb back in, seal the hatch, rest for a few hours, and fire the ascent engine to return to lunar orbit and rendezvous with Collins. Here's the thing about that ascent engine. It had to work. There was no backup. If it didn't ignite, Armstrong and Aldrin would die on the moon, and there was nothing anyone could do about it. The engine was designed to be as simple and reliable as possible. Hypergolic propellants, meaning the fuel and oxidizer ignite on contact, no ignition system needed. Aerozyne 50 and nitrogen tetroxide. You mix them, they burn. That simplicity was a deliberate engineering choice driven by the absolute necessity of reliability. And it worked. It worked every single time it was ever fired, on every Apollo mission. They dock with Columbia, transfer the samples and themselves, jettison the lunar module, and burn for home. On July 24th, the command module hits Earth's atmosphere at about 25,000 miles per hour. The heat shield ablating away as designed, temperatures on the exterior reaching around 5,000 degrees Fahrenheit. Parachutes deploy. They splash down in the Pacific. It's over. They did it. Kennedy's deadline, set in May of 1961 with only 15 minutes of spaceflight experience behind it, has been met with 5 months to spare. And the engineering achievement is almost incomprehensible in its scope. The Apollo program at its peak employed around 400,000 people across 20,000 companies and universities. The total cost, adjusted to today's dollars, was somewhere around $200 to $260 billion. It remains one of the largest peacetime mobilizations of engineering talent in human history. But Apollo didn't stop with 11, and the later missions, the ones most people don't remember as well, were in many ways more scientifically valuable. Apollo 12, in November 1969, demonstrated precision landing. Pete Conrad put the lunar module down within walking distance of the Surveyor 3 probe that had landed 2.5 years earlier. They actually retrieved parts of Surveyor and brought them home for analysis. Apollo 13, in April 1970, never landed on the moon at all, and we should talk about that, because it's one of the great engineering stories of survival. About 56 hours into the flight, roughly 200,000 miles from Earth, astronaut Jack Swigert flipped a switch to stir the cryogenic oxygen tanks in the service module. One of those tanks, oxygen tank number 2, had been damaged long before the flight. It had been dropped during manufacturing, and later, during a ground test, a heater inside the tank had been accidentally run at 65 volts instead of the intended 28 volts, which damaged the Teflon insulation on the internal wiring. Nobody caught it. So when Swigert stirred the tank, the damaged wiring short-circuited, the oxygen ignited, and the tank exploded. It blew out an entire panel of the service module and damaged the other oxygen tank as well. Within about 3 hours, both oxygen tanks were empty. This was catastrophic. The fuel cells that generated electricity for the command module ran on hydrogen and oxygen. No oxygen, no power. The command module was dying. Commander Jim Lovell, Jack Swigert, and Fred Hayes had to power down the command module almost completely and move into the lunar module Aquarius, using it as a lifeboat, something it had never been designed to do. The lunar module had its own oxygen, its own batteries, its own engine. But it was built to support 2 people for about 45 hours on the lunar surface, and now it had to support 3 people for roughly 90 hours on the trip back to Earth. The engineering challenges were staggering. Carbon dioxide was building up because the lunar module's lithium hydroxide canisters couldn't handle the load of 3 people for that long. The command module had plenty of spare canisters, but they were square, and the lunar module's receptacles were round. So, engineers on the ground, working with only the materials known to be available on the spacecraft, cardboard, plastic bags, duct tape, hose from the spacesuits, improvised an adapter. They talked the crew through building it, step by step, and it worked. The CO2 levels dropped. Navigation was another problem. They needed to do precise engine burns to get back on a trajectory that would hit Earth's atmosphere at exactly the right angle. Too shallow, and they'd skip off into space. Too steep, and they'd burn up. They used the lunar module's descent engine for a critical burn, manually aligning the spacecraft using the Earth's terminator line as a reference because the normal star tracking systems were fouled by a cloud of debris surrounding the spacecraft. Power was desperately low. The cabin temperature dropped to near freezing. Condensation formed on every surface. The astronauts were cold, exhausted, dehydrated. But on April 17th, they jettisoned the service module, and for the first time saw the damage, an entire panel blown away, wiring and debris hanging out. Then they powered up the command module using a carefully sequenced procedure that engineers had worked out in just days, something that normally would have taken months to develop and test. They jettisoned the lunar module, entered the atmosphere, and splashed down safely. All 3 survived. and the investigation that followed traced the whole disaster back to that dropped tank, that overheated wire, that missed inspection. A chain of small oversights that cascaded into a crisis 200,000 miles from home. It's a textbook case of how complex systems fail, not from one big, obvious mistake, but from multiple small ones lining up in exactly the wrong way. Apollo 14 through 17 continued through early 1972. The later missions carried the Lunar Rover, an electric vehicle that let astronauts explore miles from the landing site. Apollo 15, 16, and 17 were the J missions, designed for extended stays and serious science. Harrison Schmitt on Apollo 17 was the only professional geologist to walk on the moon, and his trained eye spotted the famous orange soil at Shorty Crater, tiny glass beads from ancient volcanic eruptions that told scientists volumes about the moon's geological history. Gene Cernan, also on Apollo 17, was the last person to walk on the moon in December 1972. As of now, more than 50 years later, no one has been back. And that's a strange thing to sit with, isn't it? We went to the moon 6 times. 12 people walked on its surface, and then we stopped. The reasons were mostly political and economic. The Vietnam War was draining budgets and public patience. The Apollo program had achieved its political goal, beating the Soviets, and the scientific returns, while genuinely valuable, weren't enough to justify the enormous cost in the eyes of Congress. Apollo 18, 19, and 20 were all canceled. The hardware had already been built. Saturn V rockets that could have flown to the moon ended up as museum displays. But even as Apollo was winding down, NASA was already pivoting toward something different. A reusable spacecraft that could make access to low Earth orbit routine and affordable. At least, that was the idea. The Space Shuttle program began taking shape in the early 1970s, and the engineering philosophy behind it was fundamentally different from anything that had come before. Instead of throwing away your rocket after every flight, you'd build a vehicle that could fly to orbit, come back, land like an airplane, and fly again within weeks. That was the dream, anyway. And on paper, it sounded like the obvious next step. You've proven you can get to space. Now, make it practical. Make it a truck, not a sports car. Make it something that works Monday through Friday, not just for a handful of heroic missions. But here's the thing about the Space Shuttle. The vehicle that actually got built was a compromise, and not a small one. It was a compromise between what NASA wanted, what the Air Force wanted, and what Congress was willing to pay for. And understanding those compromises is really important because they shaped everything about the shuttle, including its triumphs and its tragedies. So let's talk about what happened. In the late 1960s and early 1970s, NASA studied dozens of possible designs for a reusable spacecraft. The most ambitious concepts were fully reusable. A 2-stage system where a big crewed booster would carry a smaller orbiter on its back, fly to a certain altitude and speed, separate, and then both vehicles would fly home and land on runways. No expendable parts at all. Every piece comes back. That's the purest version of the idea, and from a long-term economic standpoint, it makes the most sense. But the development cost was staggering. You'd essentially be building 2 brand new spaceplanes simultaneously, and in the post-Apollo budget climate, Congress wasn't going to fund that. So NASA started trimming. The fully reusable booster got replaced by expendable external propellant tanks, then by a single large external tank. The Air Force got involved, because NASA needed their support to justify the program to Congress, and the Air Force had their own requirements. They wanted a vehicle with a huge payload bay, big enough to carry their largest reconnaissance satellites, and they wanted the ability to launch from Vandenberg Air Force Base in California into polar orbit, do one orbit, deploy a satellite, and glide back to land at Vandenberg. That single orbit polar mission requirement drove the shuttle's cross-range capability, meaning how far it could steer sideways during re-entry, and that cross-range requirement is what gave the orbiter those big delta wings. Without the Air Force requirement, the shuttle might have had smaller, stubbier wings, which would have been lighter and simpler. But the deal was the deal. NASA needed the Air Force's political support, and the Air Force needed those big wings. The design that emerged by the mid-1970s was what we ended up with, an orbiter roughly the size of a DC-9 airliner, with a 60-foot-long payload bay that could carry about 50,000 pounds to low Earth orbit. The orbiter had 3 main engines, called the Space Shuttle Main Engines, or SSMEs, which burned liquid hydrogen and liquid oxygen fed from a giant external tank, that big orange tank you see in every launch photo. The external tank was the one major piece that wasn't reused. It would be jettisoned just before reaching orbit and burn up over the ocean. And then, strapped to the sides of that external tank, 2 solid rocket boosters, the largest solid-fuel rockets ever flown, providing most of the thrust for the first 2 minutes of flight. Now, those solid rocket boosters are worth spending some time on, because they represent one of the most consequential engineering decisions in the whole program. Solid rockets are mechanically simple. There are no turbopumps, no plumbing, no valves. You basically have a giant tube packed with a rubbery propellant mixture. You light one end, and it burns until it's done. You can't throttle them. You can't shut them down. Once they're lit, they're going. That simplicity is appealing from a manufacturing standpoint, but it comes with a serious trade-off. If something goes wrong with a solid rocket during flight, there's nothing you can do about it. With a liquid engine, you can shut it down. With a solid, you're committed. The boosters were built by Thiokol Chemical Corporation in Utah, and because they were so large, about 149 feet tall, they couldn't be manufactured as single pieces and shipped by road. So they were cast in segments, 4 main segments per booster, and those segments were shipped by rail to Kennedy Space Center, where they were stacked and joined together using Tang and Clevis joints sealed with rubber O-rings. Remember that detail. The O-rings. We'll come back to them. The orbiter itself was a remarkable piece of engineering. Those 3 main engines were, pound for pound, some of the most efficient and high-performance rocket engines ever built. Each one produced about 375,000 pounds of thrust at sea level, and they operated at chamber pressures and temperatures that pushed the absolute limits of material science. The turbopumps inside those engines spun at something like 37,000 revolutions per minute, moving fuel and oxidizer at enormous flow rates. And unlike the Saturn V's F1 engines, which were used once and thrown into the ocean, the SSMEs were designed to be reused for dozens of flights. That reusability requirement meant they had to be built to incredibly tight tolerances, and they had to be inspected and refurbished between every mission. It made them expensive and labor-intensive, which was sort of the opposite of what the reusability concept was supposed to achieve. And then, there's the thermal protection system, the heat shield. This was one of the shuttle's most distinctive and most problematic features. When the orbiter re-enters the atmosphere, it's coming in at about 17,500 miles per hour, and the air in front of it compresses and heats to temperatures above 2,300 degrees Fahrenheit on the hottest surfaces. The Apollo capsules handled this with an ablative heat shield, a material that chars and erodes away, carrying the heat with it. Simple, effective, but single use. The shuttle needed something reusable, so engineers developed a system of silica tiles, about 24,000 of them on each orbiter, individually shaped and bonded to the vehicle's aluminum skin. Each tile was unique, fitted to its specific location. They were incredibly good insulators. You could heat one side to glowing white hot and touch the other side with your bare hand. But they were also fragile. They were basically high-tech ceramic foam, and they could be damaged by impacts, by handling, by rain. Maintaining those tiles between flights was a massive, painstaking job, and it was one of the reasons the shuttle never achieved the quick turnaround times NASA had originally promised. The first orbiter, Enterprise, was built without engines or a functional heat shield. It was used only for atmospheric glide tests in 1977, dropped from the back of a modified 747 to prove the vehicle could land as an unpowered glider. And that's another thing worth appreciating. The shuttle came home dead stick every single time, no engines during landing. It was a glider with the aerodynamic profile of a brick, coming in at a steep angle at over 200 miles per hour, and the pilot got exactly one chance to land. No go-arounds. If you missed the runway, that was it. The test pilots who flew those approach and landing tests said it handled surprisingly well, but the margins were tight. Columbia, the first flight-capable orbiter, launched on April 12, 1981, exactly 20 years to the day after Gagarin's flight, which was a nice piece of symbolism. The mission was STS-1, crewed by John Young, who was one of the most experienced astronauts in history. He'd flown Gemini, he'd orbited the moon on Apollo 10, he'd walked on the moon on Apollo 16, and Bob Crippen, a rookie who'd been waiting years for his first flight. Think about the audacity of that first mission. It was the first time the shuttle flew to space, and it had a crew on board. There was no uncrewed test flight first. Every other American crewed spacecraft, Mercury, Gemini, Apollo, had been tested without people before anyone climbed aboard. But the shuttle was so complex, and the solid rocket boosters couldn't be tested in a full-up configuration without actually flying. So NASA decided to put astronauts on the very first orbital flight. Young and Crippen rode Columbia to orbit, spent 2 days testing systems, and glided to a landing at Edwards Air Force Base in California. It worked. Over the next few years, the shuttle fleet grew: Challenger, Discovery, Atlantis, and the flight rate climbed. NASA had originally projected the shuttle would fly up to 50 missions a year, which seems almost laughable in hindsight. The actual peak was 9 flights in 1985. The turnaround time between flights was months, not weeks. The cost per flight, when you factored in the standing army of engineers and technicians needed to process and maintain the vehicles, ended up being far higher than expendable rockets. The shuttle was many things: capable, versatile, an extraordinary piece of engineering, but cheap and routine it was not. And then came January 28, 1986. It was an unusually cold morning at Kennedy Space Center, with temperatures dropping below freezing overnight and icicles hanging from the launch pad. Challenger was scheduled for its 10th flight, STS-51L, carrying a crew of 7, including Krista McAuliffe, a schoolteacher from New Hampshire who'd been selected for NASA's Teacher in Space program. Millions of school children were watching the launch on live television. 73 seconds after liftoff, Challenger broke apart. The cause, as the subsequent investigation led by the Rogers Commission revealed, traced back to those O-rings in the solid rocket booster joints. The rubber O-rings were designed to flex and seal the gap between booster segments as the joint flexed under the enormous pressure of ignition. But rubber gets stiff when it's cold. Engineers at Thiokol had actually raised concerns the night before the launch, arguing that the O-rings had never been qualified for temperatures as low as what was forecast that morning, around 36 degrees Fahrenheit at the joint. They recommended delaying the launch. But under pressure from NASA managers who were frustrated by repeated delays and eager to maintain the flight schedule, Thiokol management overruled their own engineers and gave the go-ahead. On that cold morning, the O-ring in the right solid rocket booster's aft field joint failed to seal properly. Hot combustion gases, around 5,000 degrees, burned past the O-ring almost immediately at ignition, creating a plume of flame that eventually reached the external tank. The tank ruptured, the hydrogen and oxygen mixed and ignited, and the aerodynamic forces tore the vehicle apart. The crew cabin remained largely intact through the breakup and continued on a ballistic arc, reaching an altitude of about 65,000 feet before falling into the Atlantic Ocean. At least some of the crew survived the initial breakup. 3 of the 4 emergency air packs that were recovered had been manually activated. They were conscious, at least for a time, during the nearly 3-minute fall to the ocean. The impact with the water was not survivable. 7 people died because a rubber seal got cold, and a management chain prioritized schedule over engineering judgment. The physicist Richard Feynman, who served on the Rogers Commission, famously demonstrated the O-ring problem during a televised hearing by dunking a piece of the O-ring material in a glass of ice water and showing how it lost its resilience. It was a simple, devastating demonstration of a simple, devastating failure. The shuttle program was grounded for nearly 3 years. The boosters were redesigned with an additional O-ring and heater systems on the joints. NASA's management culture was supposed to change, more emphasis on safety, more willingness to listen to engineers raising concerns. And for a while, it did. Flights resumed in 1988 with Discovery's STS-26 mission, and the shuttle went on to do genuinely remarkable things. It deployed the Hubble Space Telescope in 1990, then serviced it 5 times over the following years, turning what was initially an embarrassment. Hubble's primary mirror had been ground to the wrong shape, producing blurry images, into one of the most productive scientific instruments in history. Shuttle astronauts literally installed corrective optics in orbit, like fitting the telescope with glasses. The shuttle carried components of the International Space Station into orbit and assembled them, piece by piece, over more than a decade of construction flights starting in 1998. It was genuinely the only vehicle in the world that could do that kind of work, carry massive modules in its payload bay, dock with the station, and provide astronauts with a robotic arm and the ability to do complex spacewalks. But the fundamental vulnerabilities of the design never went away. And on February 1st, 2003, Columbia, the very first orbiter, the one John Young and Bob Crippen had flown 22 years earlier, was lost during re-entry. 82 seconds after launch, 16 days before, a briefcase-sized piece of insulating foam had broken off the external tank and struck the leading edge of Columbia's left wing. It punched a hole in one of the reinforced carbon-carbon panels that protected the wing's leading edge during the searing heat of re-entry. When Columbia re-entered the atmosphere over Texas, superheated plasma entered the wing through that hole, melted the aluminum structure from the inside, and the wing failed. The vehicle broke apart at an altitude of about 200,000 feet, traveling at 18 times the speed of sound. All 7 crew members were killed, And here's what makes the Columbia disaster so haunting. Engineers at NASA had noticed the foam strike during the mission. They'd seen it on launch footage. They requested high-resolution imagery, possibly from military satellites, to assess the damage. But NASA management declined the request. The foam had struck on previous flights without catastrophic results, and a kind of normalization of deviance had crept in. The same cultural pattern that had contributed to Challenger. Something dangerous was happening regularly, and because it hadn't caused a disaster yet, it was reclassified from a safety concern to an acceptable risk. Until it wasn't. The Columbia Accident Investigation Board's report was scathing, not just about the technical failure, but about the organizational culture that allowed it. The shuttle flew for another 8 years after Columbia, completing the International Space Station, but its retirement was already decided. The last shuttle mission, STS-135, flew in July 2011. Atlantis landed at Kennedy Space Center, rolled to a stop, and the program was over. 135 missions, 2 catastrophic losses, 14 crew members killed, an extraordinary vehicle that never quite became what it was supposed to be. But even while the shuttle was still flying, a different kind of revolution was quietly beginning, one that would fundamentally change who builds rockets and how much it costs to reach orbit. And it started, of all places, with a guy who'd made his fortune selling software on the internet, Elon Musk. He'd co-founded PayPal, sold it to eBay in 2002 for about $1.5 billion, and walked away with somewhere around $165 million after taxes. And instead of doing what most newly minted tech millionaires do, buying islands, retiring early, maybe angel investing from a beach house, Musk decided he wanted to go to Mars. Not metaphorically, literally. He wanted to put a greenhouse on Mars, grow a plant in Martian soil, and beam the image back to Earth to reignite public enthusiasm for space exploration. That was the original idea. Pretty modest, actually, compared to what came later. So he started looking into how much it would cost to buy a rocket. He flew to Russia, twice, to negotiate purchasing refurbished ICBMs, old Dnepr rockets that had been decommissioned after the Cold War. The Russians quoted him something like $20 million per rocket, and Musk thought that was absurd. On the flight home from that second trip, he reportedly opened a spreadsheet on his laptop and started calculating the raw cost of the materials that go into a rocket: the aluminum, the steel, the fuel, the avionics. And he realized that the cost of the raw materials was roughly 2% of the price he was being quoted. 2%. The other 98% was overhead, inefficiency, cost plus contracting, and decades of institutional inertia. And that's when the idea shifted. He didn't need to buy a rocket. He needed to build a rocket company. SpaceX was founded in June 2002 in a warehouse in El Segundo, California, right near Los Angeles International Airport. And from the very beginning, Musk's approach was different from anything the aerospace industry had seen. He hired young engineers, many of them straight out of college or poached from places like Boeing and TRW, and he told them to question every assumption. Why does a turbopump cost this much? Why does it take this long to machine a fuel injector? Can we make this part ourselves instead of buying it from a subcontractor who buys it from another subcontractor? This was the key insight, and it sounds simple, but it was genuinely radical in aerospace. Vertical integration. Instead of contracting out hundreds of components to dozens of suppliers, each adding their own margin and their own delays, SpaceX would manufacture as much as possible in-house. They'd make their own engines, their own avionics, their own structures. They'd control the whole process. Their first rocket was the Falcon 1, a small, two-stage vehicle designed to carry about 670 kilograms to low Earth orbit. And here's where the story gets humbling, because SpaceX's early years were brutal. The first Falcon 1 launch happened in March 2006 from Kwajalein Atoll, in the Marshall Islands, way out in the Pacific. It failed 25 seconds after liftoff. A corroded fuel line nut, a tiny, cheap component, caused an engine fire that brought the whole thing down. The second launch, in March 2007, reached space, but the upper stage developed a roll oscillation and failed to reach orbit. The third launch, in August 2008, was the one that nearly killed the company. The first stage performed perfectly, but when the stages separated, residual thrust from the first stage caused it to bump into the second stage. The payload was lost. 3 launches, 3 failures, and SpaceX was running out of money. Musk later said the company had enough funding for one more attempt. If the fourth launch failed, SpaceX was done. Think about that for a second. Everything that SpaceX would eventually become, the Falcon 9, the Dragon capsule, crew missions to the space station, Starship, all of it hinged on one more launch from a tiny island in the Pacific. The fourth Falcon 1 launched on September 28, 2008, and it worked. It reached orbit perfectly, becoming the first privately developed liquid-fueled rocket to do so. Musk reportedly broke down in tears. Within weeks, NASA awarded SpaceX a $1.6 billion contract under the Commercial Resupply Services program to fly cargo to the International Space Station. The company survived. But SpaceX wasn't the only player in this new commercial space revolution. There was also a quieter, more methodical effort happening on the other side of the country. Jeff Bezos, the founder of Amazon, had started a company called Blue Origin back in 2000, actually 2 years before SpaceX. Blue Origin's motto was Gradatim Ferociter, Latin for step by step, ferociously. And Bezos meant it. Where Musk was public, brash, and moved at breakneck speed, Bezos was secretive and patient. Blue Origin spent years developing technology behind closed doors at a test facility in West Texas, barely saying anything publicly. They were working on vertical takeoff, vertical landing vehicles, the same reusability concept that would later become SpaceX's signature. But they were approaching it more cautiously. And then there was the government side of this transition. NASA, after the Columbia disaster, had been directed by President George W. Bush in 2004 to retire the shuttle and develop a new vehicle to return astronauts to the moon. This became the Constellation program, the Ares 1 crew launch vehicle, the Ares 5 heavy lifter, and the Orion crew capsule. But Constellation was plagued by budget problems and schedule delays. When the Obama administration took office in 2009, they commissioned a review, the Augustine Committee, which concluded that Constellation was on an unsustainable path. In 2010, Obama effectively canceled Constellation, but kept the Orion capsule and directed NASA to develop a new heavy-lift rocket, which became the Space Launch System, or SLS. And critically, the Obama administration doubled down on commercial crew, the idea that NASA should buy rides to the space station from private companies rather than building and operating its own vehicles. This was a genuine philosophical shift. For 50 years, NASA had been the designer, builder, and operator of American crewed spacecraft. Now they were becoming a customer, and not everyone was happy about it. There were fierce congressional battles because the traditional approach, cost-plus contracts with big aerospace companies like Boeing and Lockheed Martin, funneled money into specific congressional districts. The commercial approach threatened that. But NASA moved forward with the Commercial Crew Program, and in 2014 they awarded contracts to 2 companies, SpaceX, with its Crew Dragon capsule, and Boeing, with its CST-100 Starliner. Now here's where the story gets really interesting from an engineering standpoint. SpaceX had been working on something that most of the aerospace industry thought was somewhere between impractical and impossible: landing an orbital-class rocket booster vertically, so it could be reused. The idea itself wasn't new. The DCX, a small experimental vehicle built by McDonnell Douglas in the early 1990s, had demonstrated vertical landing, but nobody had done it with a booster that had actually delivered a payload to orbit and then come back. The engineering challenges were enormous. You're taking a first stage that's about 47 meters tall, that's been traveling at several thousand miles per hour, and you need to flip it around, reignite its engines, guide it back to a precise landing spot, either a pad on land or a drone ship floating in the Atlantic, and set it down on 4 landing legs with a final suicide burn, meaning the engine thrust is greater than the weight of the nearly empty stage, so you can't hover. You get one shot. You either nail the landing or you don't. SpaceX tried and failed, multiple times. They started attempting booster landings in 2013, and the early tests were spectacular in the way that rocket failures always are. Boosters coming in too fast, too tilted, running out of hydraulic fluid for the grid fins, tipping over on the drone ship, and exploding in fireballs that SpaceX, to their credit, compiled into a blooper reel they actually released publicly. But each failure taught them something. Each attempt got closer. And on December 21st, 2015, a Falcon 9 first stage landed vertically at Landing Zone 1 at Cape Canaveral. It was the first time an orbital-class booster had been recovered intact after delivering a payload to orbit. The webcast footage is remarkable. This tall, slender rocket descending on a column of flame, settling onto the pad, the engines cutting off, and then just standing there, upright, intact, ready, in principle, to fly again. And they did fly them again. The first reflight of a recovered booster happened in March 2017, and over the following years, reuse became routine. Some Falcon 9 boosters have now flown more than 20 times each. Think about what that means economically. A Falcon 9 launch costs SpaceX's customers somewhere around $67 million, and that price has been coming down. Before SpaceX, a comparable launch on a United Launch Alliance Atlas V might cost $150 to $200 million. SpaceX cut the cost of access to orbit roughly in half, and with full reuse of the booster, their internal costs are even lower. This is the revolution. Not just a new rocket, but a new economic model for spaceflight. And SpaceX kept pushing. In February 2018, they launched the Falcon Heavy for the first time. Essentially, 3 Falcon 9 first stages strapped together, making it the most powerful operational rocket in the world at that time. The test payload was Musk's personal Tesla Roadster, with a mannequin in a spacesuit at the wheel, playing David Bowie's Space Oddity on loop. It was absurd and theatrical, and exactly the kind of thing that made traditional aerospace people roll their eyes. But the 2 side boosters landed simultaneously at Cape Canaveral, touching down in perfect synchrony, and even the skeptics had to admit it was breathtaking. Meanwhile, on May 30th, 2020, SpaceX launched astronauts Doug Hurley and Bob Behnken to the International Space Station aboard Crew Dragon, the first crewed orbital mission launched from American soil since the final shuttle flight 9 years earlier. NASA had been buying seats on Russian Soyuz capsules in the interim, at roughly $80 million per seat. The Crew Dragon mission marked the first time a commercially built and operated spacecraft carried humans to orbit. And the capsule itself was a striking piece of engineering. Sleek, with touchscreen controls replacing the banks of physical switches that had defined every previous American spacecraft. The astronauts could fly it manually if needed, but the entire rendezvous and docking sequence with the station was automated. Boeing's Starliner, by contrast, had a rougher path. Its first uncrewed test flight in December 2019 suffered a mission-elapsed timer error. The spacecraft's clock was off by about 11 hours, which caused it to burn through its maneuvering fuel, thinking it was at a different point in its mission profile. It never reached the station. A second uncrewed test in May 2022 succeeded, but the first crewed test flight didn't happen until June 2024, and even then, it experienced helium leaks and thruster issues that kept the astronauts at the station far longer than planned. The contrast between SpaceX's iterative, fail-fast approach and Boeing's traditional aerospace development process became a case study in how different engineering cultures produce different outcomes. But Commercial Crew was just one thread in a much larger tapestry of what was happening in space during this period. Because while SpaceX was landing boosters and Boeing was debugging Starliner, something else extraordinary was unfolding. A robotic exploration program that was quietly rewriting our understanding of the solar system. And one mission in particular, a little rover that landed on Mars in August 2012, would end up doing something no one expected. It would find evidence that Mars was once a place where life could have survived. Curiosity, officially the Mars Science Laboratory, touched down in Gale Crater on August 6, 2012, using a landing system so audacious that the engineers who designed it half-jokingly called it the Sky Crane. And honestly, when you hear how it works, you understand why people thought they were out of their minds. The rover weighed about 900 kilograms, roughly the size of a small car. That's way too heavy for the airbag bouncing technique that had worked for the smaller Spirit and Opportunity rovers back in 2004. So the Jet Propulsion Laboratory team came up with something that had never been tried before. The spacecraft would enter the Martian atmosphere protected by a heat shield, then deploy a supersonic parachute to slow down, then drop the heat shield away, then fire retro rockets to hover, and then, here's the part that made everyone nervous, lower the rover on cables from the hovering descent stage, like a crate being lowered from a helicopter, gently setting it down on its wheels on the surface. And then the descent stage would cut the cables and fly away to crash at a safe distance. The whole sequence from atmospheric entry to touchdown took about 7 minutes, all of it autonomous, because the signal delay between Earth and Mars meant the rover had already either landed or crashed by the time anyone at JPL even knew the sequence had started. They called it the 7 minutes of terror. And that wasn't marketing hype. It was a genuine description of what it felt like to sit in mission control and wait. And it worked. Perfectly. Curiosity rolled onto the floor of Gale Crater and started doing what it was built to do, analyzing rocks, drilling into the surface, sniffing the atmosphere. Within its first year, it found something remarkable. The rocks in an area called Yellowknife Bay contained clay minerals that only form in the presence of water that's not too acidic, not too alkaline, water you could have scooped up and drunk, more or less. The chemistry showed traces of sulfur, nitrogen, oxygen, phosphorus, carbon, the key building blocks that life as we know it requires. Curiosity hadn't found life. That's an important distinction. But it had found that Gale Crater was once the bed of a freshwater lake, billions of years ago, and that the conditions there would have been entirely hospitable to microbial life. That was the mission's primary scientific objective, answered in the affirmative. Mars was once habitable. And Curiosity kept going. As of now, it's been operating for over a decade, far beyond its planned 2-year mission. It climbed the slopes of Mount Sharp, the enormous central peak of Gale Crater, reading the geological history of Mars layer by layer, like reading the pages of a book written in stone. Each layer told a different story: wet periods, dry periods, transitions. The picture that emerged was of a planet that had been warm and wet for sustained periods, not just briefly, but long enough for complex chemistry to have played out. Now, Curiosity had a successor. In February 2021, NASA landed Perseverance in Jezero Crater, a site chosen specifically because orbital images showed what looked like an ancient river delta, a fan-shaped deposit of sediment where a river once flowed into a lake. If you were looking for signs of ancient microbial life on Mars, a river delta is exactly where a biologist would tell you to look. Perseverance carried more sophisticated instruments than Curiosity, including a device called Sherlock that could scan rocks with an ultraviolet laser to detect organic molecules, and a caching system designed to seal rock samples in small titanium tubes and leave them on the surface for a future mission to pick up and bring back to Earth. That future mission, Mars Sample Return, has been one of the most debated programs in NASA's recent history, with ballooning cost estimates pushing past $11 billion and timelines stretching into the 2030s. But the underlying idea is extraordinary: bringing pieces of Mars to laboratories on Earth where they can be analyzed with instruments far too large and sensitive to send on a spacecraft. Perseverance also carried a small technology demonstration that captured the world's imagination in a way that the rock samples didn't. Tucked underneath the rover's belly was Ingenuity, a tiny helicopter weighing just 1.8 kilograms. The challenge of flying on Mars is staggering. The atmosphere is only about 1% as dense as Earth's, so there's almost nothing for rotor blades to push against. To generate lift in that thin air, Ingenuity's blades had to spin at around 2,400 revolutions per minute, much faster than a helicopter on Earth. On April 19, 2021, Ingenuity lifted off the Martian surface, hovered at about 3 meters for 30 seconds, and landed. It was the first powered, controlled flight on another planet. The Wright brothers' first flight at Kitty Hawk lasted 12 seconds and covered about 37 meters. Ingenuity's first flight was similarly modest and similarly historic. A small piece of fabric from the Wright Flyer was actually attached to Ingenuity, a quiet tribute to the connection between those two moments. Ingenuity was designed for 5 flights over 30 days. It ended up completing 72 flights over nearly 3 years before a rotor blade was damaged in January 2024. But Mars wasn't the only destination drawing robotic explorers during this period. Let's talk about the outer solar system for a moment, because some of the most profound discoveries of the last 2 decades came from places much farther away. The Cassini spacecraft, which arrived at Saturn in 2004, spent 13 years studying the ringed planet and its moons. And what Cassini found at a small moon called Enceladus changed the way scientists think about where life might exist. Enceladus is tiny, only about 500 kilometers across, small enough to fit inside the borders of Arizona. But Cassini observed enormous plumes of water vapor and ice particles erupting from cracks near its south pole, geysers shooting material hundreds of kilometers into space. By flying through those plumes and analyzing the particles, Cassini detected not just water, but salt, silica nanoparticles, and simple organic molecules. The silica particles were particularly telling. They indicated hydrothermal activity on the ocean floor, hot water reacting with rock. The same kind of chemistry that happens at hydrothermal vents on Earth's ocean floor. And those vents on Earth are teeming with life, thriving in total darkness, powered not by sunlight, but by chemical energy. So here's this tiny ice moon orbiting Saturn, 1 billion miles from the Sun, and it has a global ocean of liquid water beneath its icy shell, heated by tidal forces as Saturn's gravity flexes and squeezes the moon's interior. And that ocean has the chemistry, water, energy, organic molecules that could potentially support life. Not complex life, probably, but microbes, maybe. Cassini couldn't answer that question definitively, but it reframed where we should be looking. The old assumption was that you needed to be in the habitable zone, that Goldilocks distance from a star where liquid water can exist on the surface. Enceladus blew that assumption apart. You can have liquid water far from any star, as long as you have another energy source. Tidal heating works just fine. Cassini's mission ended in September 2017 in one of the most poignant moments in space exploration history. The spacecraft was running low on fuel, and NASA couldn't risk it eventually crashing into Enceladus or Titan, another moon with its own fascinating chemistry, and potentially contaminating those worlds with Earth microbes. So, they deliberately plunged Cassini into Saturn's atmosphere, where it burned up. In its final minutes, it transmitted data about the composition of Saturn's upper atmosphere, doing science right up until the signal went dead. The mission team called it the grand finale, and many of them cried. 13 years with a spacecraft, you develop a relationship with it. Meanwhile, even farther out, NASA's New Horizons probe reached Pluto in July 2015 after a 9.5-year journey, giving us our first close-up images of that distant world. And Pluto turned out to be far more geologically active and complex than anyone expected, with mountains of water ice, vast nitrogen ice plains, and a thin atmosphere. But let me bring things back closer to home, because the story of space exploration in the 2020s isn't just about robots on distant worlds. It's about a renewed push to send humans beyond low Earth orbit for the first time since Apollo. NASA's Artemis program, which grew out of the SLS and Orion systems that had been in development since the Obama era, is aimed at returning astronauts to the lunar surface. Artemis 1 launched in November 2022, an uncrewed test flight that sent the Orion capsule around the moon and back, a journey of about 1.4 million miles over 25 days. The SLS rocket, despite years of cost, overruns and delays, it's essentially built from shuttle-derived hardware, including the same RS-25 engines that powered the orbiter, performed well. Artemis 2, planned to carry astronauts around the moon without landing, has been in preparation, while Artemis 3 aims to put boots on the lunar surface using a SpaceX Starship variant as the landing vehicle. And that choice, using Starship, is itself a fascinating engineering story, because Starship is the most ambitious rocket ever attempted. Fully stacked with its super heavy booster, it stands about 120 meters tall, taller than the Saturn V, and is designed to be fully reusable. Both stages are meant to return and land. The entire vehicle is built from stainless steel rather than the aluminum lithium alloys or carbon composites you might expect, because steel is cheap, easy to work with, and performs surprisingly well at both cryogenic and re-entry temperatures. It's one of those counterintuitive engineering choices that seems wrong until you think about it carefully. SpaceX has been testing Starship through a rapid, iterative process, launching prototypes, watching them explode, figuring out what went wrong, and trying again. The first integrated flight test in April 2023 ended with the vehicle tumbling and being deliberately destroyed about 4 minutes after liftoff. The launch pad itself was badly damaged because SpaceX hadn't installed a flame diverter or deluge system. They learned that lesson the hard way. But each subsequent test flew farther and achieved more. By late 2024, they had demonstrated the Super Heavy booster returning to the launch site and being caught by mechanical arms on the launch tower, a maneuver so audacious it looked like science fiction. And this is where we are now, in this strange and wonderful moment in the history of space exploration. The International Space Station, that extraordinary collaboration that has been continuously inhabited since November 2000, over 2 decades of humans living in space without interruption, is approaching the end of its operational life, with decommissioning planned for around 2030. Commercial space stations are being developed to replace it. Companies like Axiom Space are already attaching modules to the ISS that will eventually detach and become independent stations. The James Webb Space Telescope, launched on Christmas Day 2021, is peering deeper into the universe than Hubble ever could, its 6.5-meter gold-coated mirror, collecting infrared light from galaxies that formed just a few 100 million years after the Big Bang. It's finding things that challenge our models of early galaxy formation, galaxies that seem too massive, too mature for how young they are. And beyond all the hardware and the missions, something subtler has changed. Space is no longer the exclusive domain of 2 superpowers locked in a geopolitical contest. India's Chandrayaan-3 successfully landed near the moon's south pole in August 2023, making India the 4th country to soft land on the moon. Japan's SLIM lander touched down in January 2024. Private companies are attempting lunar landings. The barrier to entry has dropped, not because space got easier, but because decades of accumulated knowledge and the relentless reduction in launch costs have opened the door wider than it's ever been. Think about the arc of this story for a moment. From Babylonian astronomers scratching observations into clay tablets, trying to make sense of lights moving across the sky, through Eratosthenes measuring the Earth's circumference with a stick and a shadow, through Newton working out the mathematics of gravity, through Tsiolkovsky, alone in his log cabin, deriving the rocket equation, through Goddard launching a tiny rocket from a Massachusetts field while the newspapers mocked him, through the horror of the V2 and the moral complexity of the engineers who built it, through Korolev, who survived the gulags to put the first human in orbit, through Kennedy's impossible deadline and the 500,000 people who made it real, through the 14 astronauts who didn't come home, through the shuttle, with all its compromises and its triumphs, through a kid in South Africa reading science fiction books and deciding that humanity should be multiplanetary, and then actually building the rockets to try. It's a story about human beings doing what human beings do, looking up, wondering what's out there, and then figuring out, one problem at a time, how to go and see. Every mission, every rocket, every equation scribbled on a napkin, every test that ended in a fireball, every signal received from a spacecraft 1 billion miles away. They're all part of the same impulse, the same curiosity that made someone look at the moon and wonder if it was another world. And the beautiful thing is, the story isn't over. It's not even close to over. Right now, somewhere, an engineer is running a simulation, or bending metal, or arguing with a colleague about a design choice that might, years from now, carry someone to a place no human has ever been. The problems are enormous. Radiation exposure during long-duration missions, the physiological effects of microgravity, the sheer distances involved, the life support systems that need to work perfectly for months or years. But every one of those problems is an engineering problem. And if this whole long story has shown you anything, it's that engineering problems, given enough time and enough stubborn, brilliant people, tend to get solved. So let that thought settle over you. The same sky those Babylonian scribes watched is the same sky above you right now. The same moon that Galileo first saw through his telescope, with its craters and its mountains, is the same moon that human beings walked on and will walk on again. And somewhere out there, past Mars, past Jupiter, past the ice geysers of Enceladus, past the edge of everything we've ever explored, there's more. There's always more. And we'll get there. Slowly, imperfectly, one hard-won step at a time. But we'll get there. And for now, that's a good thought to fall asleep to.